Our next speaker is Bruce DePalma. You can start recording now, I guess, if you aren't. Okay, Bruce DePalma was born in 1935 in Orange, New Jersey, of all places. He got his Bachelor of Science at MIT, and he has degrees in electrical engineering and physics. He's done a lot of government research and development work. He's also gone to the Graduate School of Applied Physics at Harvard. He worked at Polaroid in their research department in Cambridge, Massachusetts from 1962 through 1970. He's done a lot of lecturing on photographic science concurrently, and he's done a lot of work at MIT Department of Electrical Engineering in the laboratory of Harold Edgerton. In 1970, he began the studies of some of this stuff, and the invention of the N machine came in 1977. This year he formed his own company to manufacture the N machine power generation systems. So I want to welcome Bruce DePalma.
Well, it's a pleasure to be here again and speak to a group of interesting people about an interesting subject. I am very happy to be able to talk about the N machine because I think the N machine is finally reaching a point where enough people in the world have duplicated it and discovered its properties that people are beginning to seriously think that something good might be happening. To start, I would like to thank the Tesla Society for inviting me, and I think it's a good idea to sort of invoke the spirit of Nikola Tesla to the extent that we can. And so I brought a copy of a paper which Tesla delivered in 1891, and it was published in the Electrical Engineer, New York, September 2nd, 1891. And this represents the state of our knowledge of the unipolar dynamo. It's a paragraph out of Notes on the Unipolar Dynamo by Nikola Tesla, and it goes, "It is characteristic of fundamental discoveries, of great achievements of intellect, that they retain an undiminished power upon the imagination of the thinker. The memorable experiment of Faraday, with a disk rotating between the two poles of a magnet, which has borne such magnificent fruit, has long passed into everyday existence. Yet, there are certain features about this embryo of the present dynamos and motors which even today appear to us striking, and are worthy of the most careful study. Consider, for example, the case of a disk of iron or other metal revolving between the two opposite poles of a magnet, and the polar surfaces completely covering both sides of the disk, and assume the current to be taken off or conveyed to the same by contacts, uniformly from all points of the periphery of the disk. Take first the case of a motor. In all ordinary motors, operation is dependent upon some shifting or change of the resultant of the magnetic attraction exerted upon the armature. This process being effected either by some mechanical contrivance on the motor or by the action of currents of the proper character. We may explain the operation of such a motor just as we can that of a water wheel, but in the above example of the disk surrounded completely by the polar surfaces, there is no shifting of the magnetic action, no change whatever as far as we know, and yet rotation ensues. Here then, ordinary considerations do not apply. We cannot even give a superficial explanation as in ordinary motors, and the operation will be clear to us only when we have recognized the very nature of the forces involved and fathomed the mystery of the invisible connecting mechanism." So this sets the tone of the state of our knowledge of the Faraday disk, the homopolar generator, the N machine, things like that. But long before I ever thought about N machines and electrical generators, I studied rotation. And to start off, let's have the first slide here. Can we go on that? I guess I'm the one that presses the button. Go back. Doesn't go back.
You got to reverse it on the sheet.
Okay, reverse it back. Okay, this is a machine called a force machine. And it's a machine for studying forces. Now, in physics, we have many physical theories which we use, like Einstein's theories, the theories of thermodynamics, the theories of Einstein, as applied to the motion of the planets. we have various paradigms which form the basis of these theories, like the paradigms of uniform motion versus absolute motion versus relative motion, paradigms of symmetry, paradigms of conservation, paradigms of equivalence. And all of these ideas help us to look a little further into nature, but no one of these ideas seems to describe all the phenomena. So coming into this situation in 1970 as a physicist looking at the situation of the world and the problem of the diminishing of resources and the consumption of the oil, I said to myself, there is no answer in conventional science for our energy problem. So, and I was agreed with by all the other great minds at the time. So I said to myself, well, there must be some way of looking at the facts that we already know through a different way, a different paradigm, and that might help us to do a different experiment, which will lead to knowledge. Now, one of the ideas I had, and maybe we can bring the lights up for just a second on this one here. Is that, yeah. I thought to myself, what would happen if we looked at physical phenomena from the point of view of perfection? What would that mean? Now, for instance, we know if we have a force, that this force has a magnitude and a direction. And it has a direction. Now, is that all it has? In classical physics, this is all it's supposed to have. But if we look at this pure thing, this pure force with only magnitude and direction, and ask ourselves, well, what would happen if it wasn't perfect? What would the nature of the imperfection of a force be? Now, if a force possesses magnitude and direction, my logic was that the imperfect part of something which was purely directional and had purely magnitude was something that has no direction. And the only quantity that I could think of that was totally non-directional was inertia. And so what that said to me was that if we manifested a large force, we might also manifest at the same time some inertial property, which we would have never looked for before had we not had the idea of perfection. PCTIO1, perfection. That's on candid camera. If we had the idea of perfection, then we could call this quantity, which was imperfect, the defect of forces. Okay? And the defective forces in my logical world had an inertial property associated with it. Now, going back to the first slide again, let's see how we can test this idea. So I made this apparatus, and the apparatus consists of two flywheels in a cylinder, and they're mounted in such a way as the flywheels are rotating in opposite directions. In the same plane, the axles are perpendicular to each other, and the whole precision of the apparatus is to about a 0.5/10,000th of an inch. So that in any motion of this cylinder, as it's rotated in bearings on either side, no forces developed by the flywheel can appear in the axis of precession, because they're all at right angles. I.e., that when you precess the gyroscope in this situation, the axles tend to tilt this way. And so the two top axles would press together, and the two bottom axles would pull apart, and you'd set up these forces in the walls of the cylinder. And so just simply by turning this apparatus, we create a situation where all the gyroscopic forces are canceled out, so you have an object in which you can experiment on rotation without the interference of the gyroscopic forces. And as you process the machine, forces are developed in the walls, and no reaction torque appears in the axis. Now, let's go to the next slide. This is what it looks like in reality. There are two motors, each one driving one side of the axle there, the way the flywheels look inside. This, unfortunately, is upside down, but that's how the motors and the bearings are situated on the flywheel, so to make the whole thing high precision. two needle bearings on either side and one ball bearing on the top and the bottom. Now, if you do an experiment with this apparatus and you cause it to precess and the drum of the cylinder to rotate at velocity of revolutions per second, 3.8 revolutions per second, we found that if you allowed it to slow down into a very massive load such that it was not affected by vibration or any temperature effect or anything, that it took longer for the cylinder to slow down when the flywheels are rotating inside than it did when they weren't. And there's about a 14% increase in the inertial mass of a precessing gyroscope in this experiment. Now this is very, very interesting because the only way that inertial mass is supposed to change is at light speed velocities and close to it. Here's an effect which is going on at very low speeds. These are going 10,000 RPM and precessing at 3.8 revolutions per second. So this is in the range of mechanical velocities which can be achieved on the Earth. And here's a picture of the machine now hanging in my laboratory in California. And here you can see that you can experiment on a rotating object by having the gyroscopic forces canceled. You can collide this thing with something. You can swing it back and forth as a pendulum. You can weigh it. You can do all manner of experiments on rotating objects which have never been done before. So having constructed this apparatus, I have to then proceed to start doing experiments with it. The first one was the precession experiment. And the second one, and here is what happens if you precess a little bit too fast and you crack off the 1 inch, put a little sharper focus back there. There you go. These are 1 inch diameter tool steel axles on there, and the flywheel weighs 30 pounds. And if you precess too fast, they snap right off. So now, this is one shot of an experiment. My thought was that if I got an inertial change in the force machine experiment and the precession of gyroscopes, I should be able to see the same effect just in a flywheel all by itself. Because you know when you spin a flywheel, in the wheel are manifested the forces of centripetal forces we know, or the centrifugal forces depending on how you want to look at it. These forces increase in magnitude, and if you go too fast, of course, whatever you're rotating blows up when they neutralize the forces which are holding the object together. So with the manifestation of the forces in a spinning ball bearing, here this picture is 4 feet on the bottom and 3 feet on the side high, 1 inch diameter ball bearing, like the kind you have in pinball machines. The one that goes up higher is spinning at 27,000 RPM with the axis vertical. There's a non-rotating control. They're both projected up at the same initial velocity. And careful examination of this photograph shows that the rotating object goes up higher than the non-rotating one at a slower rate of deceleration, g minus delta g, and then falls at an acceleration of g plus delta g. And this was the first simple little experiment which showed me that there might be free energy. Go on, what do you want to know?
Is that trajectory 90 degrees to your camera?
Yes, yes, yes. And the stroboscopic light flashes are at 60 cycles a second. So after I looked at this photograph for about 6 months, you know, I did go to MIT and I did go to Harvard for a little while, and I was trained in the most classical and best ways by the best people. And the idea that anything like this could happen at all was off of the spectrum of what I knew. So it took me a long time to begin to believe what I was seeing. So in the sense of extraction of energy from space, what this means is that if you had a rotating object in a box and lifted it to a height h and did a certain amount of work, the weight doesn't change of a rotating object. So the work you would need to do to lift it from the floor to a certain height wouldn't change if it was rotating or not rotating. But when you dropped it, it would drop faster and hit harder. So you could set up a cycle where you could extract energy from the gravitational field of the Earth in this process. And it's a non-conservative process. And this is the first simple archetypal physical experiment that showed me mechanically, right in front of my own eyes, that something anomalous was happening with rotating objects. Now, going on from this, somebody had to do an experiment where we got rid of the effect of the air, because people would say, well, the air is doing it. So we dropped a gyroscope in a box, protected from the air, in this setup with 2 phototransistors to time it. This was not done by me, by a couple of my students. And 15,000 RPM, rotor weight 4.75 pounds, case weight 2.48, rotor diameter 4.5 inches, total weight 7.23 pounds. This is the setup. You drop the object through the light beams, rotating and non-rotating, and then you time it. So with the results of this experiment, here to a high degree of accuracy, 5 significant figures, plus the standard deviation, and the analysis, it turns out that we have a 97% level of confidence that a fully encased spinning gyroscope drops faster than the identical gyroscope non-spinning when released to fall along its axis. Now, this is a very important experiment because what it shows is that not only what is happening to the gyroscope and affecting its rate of fall is in operation, but that same thing is happening to the case too. Because if you figure out what it would take to push on the case, a force that you would need to apply to the case to make it fall as fast as it did when it was rotating, non-rotating, you have a fictitious force of 0.38 ounces, which would have needed to be applied to the non-rotating situation to make it fall as fast as it did when it was rotating. And the fact that you don't have to apply that force in this experiment means that there's a field or some effect generated by the rotating object which is not only affecting it, but the case which is around it. So with that, we started to do experiments like this. Here we have 2 of these machines suspended from the ceiling of my living room, and there's a television camera on the left one focused on a target on the right one. Now, the experiment was a pendulum experiment where we wanted to find out that if we suspected that the rate of fall of an object was affected by its rotation, then the period of the pendulum should be affected too, because under normal circumstances, the pendulum is only dependent on the length of the cords. It doesn't depend on the weight. That's why pendulum's used for timing. But if the weight drops at a different acceleration, then the period will be affected. So we did an experiment where we wanted to set these 2 up so that they would synchronize and swing together unenergized for like 5 minutes without drifting out of phase. And then, since we knew the changes in the inertial mass were small at these low accelerations, we tried to do a differential experiment where we would start them both swinging, but one was rotating and the other was not, and we thought that they would swing out of phase with each other for a while, after a while, but what happened was that they actually dragged each other along. So we discovered right away that there was a field around the rotating object, and it could drag against an identical control object. You know, they're both the same weight, the aerodynamics of the camera and the target are the same. We did things like that. The thing was very carefully set up. The monitor is in the background. You see the target on it, the camera focused on the dummy camera. Here is an earlier setup where you can see the whole thing perfectly. And here's a thing in motion where we took the cameras away and just used a pointer, and the pointer points from one machine to the other to the target, and you can see how they start swinging out of phase in the nature of that out of phase swing, or that they drag together by observing that pointer there. Now this was a difficult experiment to do because there's a lot of mechanical variables, but it took us 2 or 3 months to get this set up. And we did videotape the dragging of one against the other, and we did notice that the TV camera, which used a Vidicom and was suspended over the rotating flywheels, that the lag in the screen increased, which meant that the inertial effect of the flywheels was affecting the recombination time of the holes in the electrons in the photocathode as well. So this is another little experiment. Then going on, this is an experiment where we started to collide them, and this is the geometry of how long the cores and things were. Here is the measurements made of the different orientations and how they swang, whether they were energized or not energized. There's 3 possible orientations of a gyroscope. It swings either along the axis or it swings in the plane of rotation. or it swings with the plane of rotation perpendicular to the surface of the Earth. And in each case, there was a slightly different swinging. And this is the result of thousands and thousands of measurements we did. Now, also what we did was the collision of the non-rotating object with the rotating one. Now, this elastic collision experiment was suggested by Edward Purcell of Harvard when we first approached him on the fact that there might be differences in the properties of rotating objects. And just to give you an idea here, that you have two machines, each one weighs two 30-pound flywheels, each machine weighs 234 pounds, collision of A into B, A released from D, and here we have motion, residual motion, total motion. Now, going through all this, the conclusions are when A is energized, B goes 1% more than when A is quiescent. So the changes we're looking at in the collision experiment are parts 100. Now what this means is in the collision of rotating atoms, where we have what we would call conservation of energy, we find that this does not apply if the mechanical model of rotation applies to the motion of atoms. So in the collision of a non-rotating object with a rotating one, or the rotating with a non-rotating one, momentum and energy are not conserved in these collisions. Now, going on, we then tried to figure out what we could do usefully with these phenomena. Now, we know, for instance, we were talking about space drives and anti-gravity earlier this afternoon. The space drive is a thing which propels itself by pushing against space itself. The anti-gravity machine is a thing which actually works against the gravitational field of the Earth and just moves away from the center of the Earth. This is a machine which depends upon the variable inertia effect of precession. So you have like the same effect you have on a screwdriver, that you push an automatic screwdriver in one direction, you get a rotation while you're pushing, and then when you pull back, there is no rotation. So while you're pushing and turning at the same time, the machine locks in space, or its inertial mass increases, and you can push against it, and then you can pull it back without rotation, and then you get low inertia. So you can create a variable inertia space drive out of the precession of a gyroscope in this manner. And the basic phenomena is the discovery that the precession of a gyroscope has a variable inertia effect, or what we call locking in space, as a mathematician called it. Let's go on now. Here is a very interesting experiment that we did, and I want to show this in a little bit more detail here. I got an idea that we had to have in any physics experiment, if you're talking about a new field or a new phenomenon, there has to be an archetypal test, which is the electron experiment or the neutron experiment, or whatever you're looking for. Well, the archetypal test for the inertial field is the bringing near the object of the tuning fork. And the tuning fork, whose motion is determined by the inertia of the tines, is affected by bringing it near a flywheel. Now, in this setup, we had an Accutron watch, which used to be made about 20 years ago in this country, used a 360 cycle fork, I think, in it, yes, with the tines arranged so they vibrated back and forth vertically along the axis. Above the 30-pound flywheel, turning 7,600 RPM, completely shielded, both of them doubly shielded. And in this setup, we synchronize the second hands, run the electric clock from the external stabilized source, and we could get a situation where the second hands tracked to the extent that after 4 hours, the Accutron was a quarter of a second faster than the clock, which was in the range of accuracy of the watch. But when you ran the flywheels, the Accutron slowed down 1 second, or almost 1 second, 9/10 of a second in 17 minutes, which is 1,000 seconds. So it's almost 1 part in 1,000 that it slowed down when operated over the axis of the flywheel. So this shows you that in the same way that if you have a charged object, the charge is in the space around the object, a hot object, the heat is in the space around the object, magnetic object, the magnetism is in the space, a radioactive object, and so forth, that the forces in the rotating object the flywheel exert an effect on the space around the object. And if the inertial mass of this rotating flywheel increases for experiments along the axis and decreases for experiments in the plane of rotation, then that same property would be imposed on anything that was moved. That is, motions of the mechanical objects in the plane of rotation near this object will have their inertia reduced, and motions in this direction will have their inertia increased. So it's a real field, and we call it the odd field. And the word OD is the old term coming from von Reichenbach in Germany, which I reinvented, just I guess like I did the end machine, invented by Faraday, but it was the name of one of my students who was with me. The O and the D are old field of DePalma, and that's why we call it the odd field. But that's what the name is I give to the inertial field of a rotating object. Now, interestingly enough, I had a thought after I read the Accutron manual, which comes with the watch. And they tell you there that if you hold a tuning fork vertical like this, it will vibrate 4.5 seconds a day faster or slower than horizontal. And they charge it off to some gravitational effect, but I said to myself, you know, I've always wondered why plants and grass and everything grow vertical. Why do they grow vertical? Is it the light that they're following? Or is it some other property? And it occurred to me there may be an inertial anisotropy to the gravitational field of the Earth, such that vibrations in the radial direction are at a slightly higher inertia than vibrations in the parallel to the surface of the Earth. So how did we test this? We got some grass and we put it in an aluminum pie plate with soil and mounted it in a piece of cardboard over a 78 RPM turntable, which was an old phonograph aluminum turntable. And we did the two experiments where we grew the grass over the turntable when it was still and when it was rotating. Now, in the rotating sense, this is what happens. And can you make that go backwards there so people can see? Non-rotating, go ahead, rotating. No, one more. Rotating. Now, interestingly enough, and I think this is true of all scientific explorations, when you are operating in the field of the unknown, you are operating with very simple equipment, and you're looking at effects which are on the level of discernibility. And that's what distinguishes scientists from non-scientists, that operating on the level of discernibility, they notice something, and then they describe an experiment to somehow bring this forth in some way, and then some new effect is discovered. So we were out in the country, and we had very simple apparatus like pendulums, tuning forks, electric clocks, grass, whole phonograph turntables, and out of this, we got some sort of interesting insights into the physics of rotation. Now, this is a graph of how the control grass grew and how the rotating grass grew, which grew a little faster. And this is the result of a summer, hours elapsed since planting the seeds, and he did a very careful study on what happened. So this is another example of something where you have to be very careful. It takes a couple of months to do, and it's the nature of physics experiments. You have to have the patience to do this. Now, another experiment we did was we swung this rotating flywheel we had near the local oscillator of an FM tuner tuned to a station 90 miles away. Now, there is no way that this was a vacuum tube local oscillator in a double Faraday cage, and the flywheel was inside 1/2 inch thick aluminum enclosure. So there was no possibility of any electric or magnetic interaction. We checked the magnetism by running an electron beam in the cathode ray tube near the apparatus. There was no effect. So just moving the rotating flywheel near the local oscillator, which depends on inductances and capacitances, and if the processes in there are somehow inertially dependent, then the frequency should shift a little bit. Now this is, for an ordinary electrical engineer who's worked on communications all his life, an effect like this is totally off the wall, but there it is, and we really, it's a 300 cycle shift at 106 megacycles, an easily measurable phenomenon. So the best we got out of Dr. Dickey at Princeton when we talked to him about this was that he knew of no experiment which could either verify this or not. He had no knowledge of this at all. So Now, another simple experiment you can do is to weigh the precessing gyroscope. Now, here is a little simple experiment you can do in your garage. You take a piece of wood, and you use a pipe cleaner as a balance, and you put a string up to the ceiling, and you hang one gyroscope on this end, and you can hang another one over there that's not rotating, balance the thing up. Then what you do is you spin the gyroscope and let it precess, and you watch what happens to the balance, and you'll see that the precessing end gets a little lighter. Now, it's very interesting that in all the history of science, nobody ever measured what a precessing gyroscope weighed, but it's one of these things. But you see, if you don't think that rotation affects anything, then you never think of doing any of these experiments. If there's nothing, terribly abstract about repeating all the experiments and mechanics on rotating objects that have been done on non-rotating ones, that's not a great insight. The big insight is to think that there might be a difference. Now, going along the lines of things getting lighter when they're precessed, you can make an anti-gravity machine like this. It's a proposed idea. Now, how to think about this? Well, we're talking about variability of inertial mass. What would happen if we looked at Newton's idea that things in motion tend to remain in motion unless acted on by an external force? Things at rest tend to remain at rest. And he said, well, let's change the sign of the inertial mass. That means things at rest would start moving, things in motion would move faster. Well, I think that the precession of a gyroscope in such wise can be understood in its anti-gravity effect as the changing of the sign of the inertial mass of the apparatus, which means it's repelled from the surface of the Earth. And we did the experiment, and we got a consistent 5-pound lightning of the precessing force machine on a scale hung from the ceiling. But when we went too fast, of course, we broke the axles as we showed. But it wasn't designed for this. It's the beginning of an effect that should be looked into. Now, after doing all these experiments on rotating objects, I started in my meditations thinking about, here's another one. Let's magnetize the rotating object and see what happens with that. So I had the intuitive feeling that we would be able to extract energy from space this way, but I didn't know as much as I know about it now. Now, this is the archetypal effect, a rotating, magnetized, conducting cylinder. That's the original effect, which I later discovered after I got onto this, that Michael Faraday had discovered this in December 31st, 1831. And this was never mentioned at MIT. This doesn't fit into the sets of equations that are supposed to describe everything there's known to be about electricity. They don't talk about this one because it's not really set as to exactly what's going on. Then you put a more refined understanding into this, and you put a conducting disk into the center of a stack of magnets, and you have what we call the N machine. And I named it the N machine because N in science means many things, like the nth degree, and I never could tell what would result from this. So N just means a lot of things will come of this. Now, this is the original notes of Faraday from December 26, 1831. A copper disc was cemented on top of a cylinder magnet, paper intervening, the top being marked, the marked pole, the magnet supported so as to rotate by means of a string, and the wires of the galvanometer connected with the edge and the axis of the copper plate. When the magnet and disc together rotated, unscrew the marked end of the needle went west. The magnet and the disc rotated, screw the marked end of the needle went east. Now this shows you real science, and you don't need big accelerators, you don't need big laboratories, you don't need big anything, you just have to have a good idea. And you see, if we stay on that level, we might make more progress. So going on, this is the conventional understanding of the Faraday disk. It's the integral of the total flux and the radius, the area of the disk, and you come up with a voltage. You got it. And this is how DePalma looks at this thing. He says, look at the universe. The universe, in my way of understanding, it has two polarities, male and female. They appear in everything we do as positive and negative, hot and cold, up and down, in and out. what would be the mechanical polarities in mechanics? They would be non-motion and motion. So how do you set up that polarization? You just rotate a flywheel and the center doesn't move and the outside does move. Now, what you do with this polarized object, well, you put it into the free energy field of the universe. And you put a magnetic field through this to convert the polarization affected mechanically into electrical polarization that converts into plus and minus. Put two contacts on there and take the electricity away. Now, maybe this is too simplistic, but consider the battery in your car. You have a lead acid battery, you take 2 plates of lead, you stick it in a beaker of dilute sulfuric acid, you apply a voltage across it, one plate turns brown, the other plate turns gray. You can take the plates away and dry them, and you have a positive plate and a negative plate, you could call them male or female. You take the plates and you stick them back into the electrolyte and you put a load and you have electricity. And so what you've created is a situation of polarized metal plates put into an electrolyte and you obtain from that energy. Here you have a condition of a polarized, magnetized plate in a sea of energy and you extract the electricity here. Now I'm not saying what the form of the sea is, I don't know what the size of the ether quanta are, I don't know anything about submolecular processes, I'm just talking about the kind of way I look at these things. So I said to some physicists in our discussions in the last few hours, I said, you know, I can explain particle physics very simply. You just create all the particles with the experiments you used to detect them with. So you devise a new experiment, you can create a new particle. It's very simple. And science is not hard. So now after that, we decided to get serious about this end machine, and of course nobody would give me any of the means that I normally was accustomed to doing these things, so we eventually went broke, like everybody that comes to California, and we got to get involved with a community of farmers, 800 farmers, 450 children, called Sunburst, one of the 3 largest agricultural communities in America. And the head of the community had a story he told that he was driving along the truck one night and a flying saucer came over and he was taken into the flying saucer and the beings on board showed him the energy machine was rotating magnets. And so when I and my men walked into this community with the rotating magnet, we saw it, we said, wow, this is what we've been waiting for. And I convinced the community from that point on to go ahead and support me, which they did. And then we built this gigantic machine with dimensions and layers of copper wire and so forth. And we put brushes on the outer edges of this plate and brushes on the axle. And then suddenly, after about a year and a half, you get this, which is the rotating electromagnet wrapped with fiberglass not to fall apart. There are 12 brushes on the outer edge of the disc, 4, 4, 4, and then there are 12 on the axis. There are 6 on the inside of this plate and 6 on the other side. And here's the current. There's 2 shunts in parallel on top, so that full-scale 800 means really 1600 amps. And in this machine, what we did was we put all the power generated into the brushes, and the brushes were used as a load, and these were these carbon graphite brushes, so they were a very low resistance load and could get hot, so we couldn't run the machine continuously, but enough to do the experiment of testing to see whether or not you did get energy out of this without having to put just as much energy in the drive over driving it. Now, here's a picture of the machine running at 6,000 RPM. It's putting out 1.5 volts at no current, and then here it is under load, 1,600 amperes at 1 volt. Now, when we did the experiment of measuring the drag, that is, by looking at a AC ammeter connected to the drive motor, we derived, originally this machine was doing a 20-to-1 or thereabouts incremental power ratio. That means for every increment of power you took out of it, you only had to put 1/20th of it into the drive motor. Later measurements made by Dr. Robert Kinchloe, Emeritus professor at Stanford, who went out to the community and took my original machine, which the community had taken away from me after we had completed because they thought they could make some money with it, And he went there, having read about this in the book about the community, the Sunburst Community book, and he asked the head of the community whether he could go there and measure it, so he did, which resulted in a report I'm sure a lot of you have seen, the Kinchloe report, where the power ratio of in changing versus out changing in this worst case condition is about 4-to-1. Depending on how you interpret it, you could, if you subtract the increase, if you don't worry about what happened, there's a phenomenon which Dr. Kinchloe discovered, that is, if you turn on a solenoid which is rotating, somehow there's a drag generated just because of the rotation of the magnet. When you turn off the solenoid, it goes away. We don't know what this is from. And if you don't worry about this, then the difference between this and that is about 7.6-to-1. So it's a clear illustration of energy from someplace, and I'd like to think of it as energy directly extracted from space. Now, going on from this, a man named Adam Trombly, who we'll probably see tomorrow or Sunday, came to see me at Sunburst. I showed him the apparatus, and he went, raised some money, and designed a variation on the original idea, which has been copied all over the world, which is the closed path machine, where instead of having the flux complete through the space, the flux is completed in a yoke around the, this is a coil, 2 coils, and this is a cylinder, and here is this is where the voltage is developed, and brushes stick in here and contact on that. Now this machine is nice because you can get high magnetic flux densities in this because the flux path is closed, but when you withdraw the current through this slot, you get a motoring action which cuts down on the gain of the machine. Now, Dr. Tewari will talk about his experiments and the power ratios that he's obtained with all kinds of different models of this idea. And this is what's going on in Germany right now, but I'll get to that too. So, put current into the disk at the edge and take it on the axle, and you find that although a torque is generated in the disk, the magnet has no reaction torque back on it and just sits there. And if anything, we can tell you there's something funny going on with the homopolar disk. This experiment should do it. So there's a lot that we don't understand about this simple rotating disk. Now, what does one want to do with a generator that produces more out than in? Well, of course, one wants to make a self-running engine. And so the idea of this was something we came up with in about 1979. It's very simple. Have the end machine on one end, and this is with the magnets rotating with the disk. On the other end, you have a Faraday disk. Can this be sharpened up a little bit? Yeah. The other end, you have a Faraday disk rotating between stationary magnets. You just connect the two together, close the switch, and it should once start keep running and produce mechanical power and electrical power. And this is a schematic of an idea. Now, we went ahead and worked on it. Here is the chassis of the machine with the 2 plates, one to enclose the Faraday disk, the other the end machine. Here is the end machine part. It's made of 5.1 inch diameter ferrite magnets. There's a copper disc in the center. The magnet's wound with graphite fibers to prevent it blowing up at high speeds. The return path is through the axle, and the axle runs on these insulated blocks. Down here is the Faraday disk. Here is a close-up of the end machine clamped in a fixture. Sticking out at that end is a mercury contact we use. Here is the mercury contact, a little cylinder filled with mercury and 2 rotating things, and it's shaped like this with the serrations. It works perfect. That's what its size is. Now there's the Faraday disk with the mercury contact on it. And so what we did, here's the early version of the machine with the disk and the end machine connected together with the solid axle. Later on, here is the machine with the mercury connection. Because we decided that it was such a complicated system that we couldn't study each part together connected. We had to separate them so we could study the Faraday disk and the end machine separately. the mercury, which is used to make the connections fed in through these tubes into the center copper cylinder, into the plates which surround each disc, and there's a slight annular separation of about 1/8 of an inch between the rotating copper disc and the hole in the plate, and the mercury amalgamates with the copper and the plate and is drawn around centrifugally and forms a bead in perfect low resistance connection with hardly any drag at all. It really works terrifically. And when the machine stops, the mercury runs out the bottom. And so when you start it, you have to wait till it gets up to a certain few hundred RPM, drop the mercury, and it stays in. Then, after you do that, here's DePalma getting ready to run this thing, and he's injecting the mercury into the end machine part. What we have here is a setup where we have a motor on the right driving the end machine. There is only an electrical connection between this part and that part. So the current from the end machine flows into the box and back into the Faraday disc here, returns back through the central axles and the mercury connection in the center. Now, the end machine generates about 1/10 of a volt at 6,000 amperes in this setup. And that 6,000 amps at 1/10 of a volt drives the Faraday disc, which drives an ordinary electrical generator backwards. I mean, it's a motor run backwards to light that bulb up there and put out about 90 volts. Now, we have a total short circuit with a clamp-on ammeter across the, here's another picture, there's the clamp-on ammeter down a little lower now. And under those conditions, you can take, and this is 340 amps, and that's only about 1/20th of the total current flowing, so you can short it with a heavy cable and nothing happens, which is an interesting effect to demonstrate to people. So this is our early work on a small model. Then what we want to do is, well, this is later. This is an equivalence engine, and it may be a little too complex for us to talk to now, but it's a higher order form of the end machine where we're talking about a self-running engine with a Faraday disc on one end and an end machine on the other. What happens if we use a torsional pendulum with the Faraday disc vibrating back and forth like this? And at this end, we have, I mean, this is the end machine on this side vibrating, the Faraday disc is on this end. And since it's a quarter wavelength between here, all this does is supply an alternating force, and there's no motion, so there's no back EMF. So it's an idea we tried, which happens to work, and it's the next higher order development of the self-running engine, but that's something we'll get into a little later. What we try to do then is to make a larger, more powerful end machine, and we start working with neodymium iron boron. These are 1 inch square, 1/2 inch thick, and then you try to make a fixture where you glue them all together. And you want to get that one in focus, and you have to move fast because this glue sets in 3 minutes. And you make a setup where you get them all pressed together, like so. And then you glue on one of the copper discs. And then you fabricate a rotor with 2 copper discs on one shaft, and the magnetic polarity is north-south, south-north. So one develops a positive voltage at the outer edge, and the other's a negative output at the outer edge, and they series through the central connecting shaft. They're wrapped with graphite to make sure that they don't blow up. And then we have little copper fingers sticking into a slot in the side of the copper plate filled with mercuries where the current's taken out. And there's the finished machine under test. And we have to build a little model before we start working on something more substantial. These are neodymium iron boron hexagons now, 2 inches across and 1 inch thick, and 3 of them are glued together here. And this little thing puts out 5.4 kilogauss right on the top of the magnet. In our machine, we're operating around 6,000 gauss, and what we do is we make a stack like that. Now this is a very, very, very difficult thing to handle, because this is intensely magnetic. This thing is solid neodymium iron, it's 200 pounds, and it's about 13 inches across. Actually, the magnets are 12 inches to one side, but it's 3 inches thick. And you can't work on this in the machine shop without using wood all the time. Every time you see wood and phenolic, it's because this is so intensely magnetic. If it ever sticks to anything or gets away from you, you can have a really dangerous accident. Now, in our machine, what we do is we have a self-energizing effect, which is an idea which Tesla had in 1891. Here we have two spirals cut in the copper disc here in parallel. Each one is 2 turns. No, I think we have 3 turns. 2 3-turn spirals. And so when you withdraw the current from the machine, you can make the incremental resistance go down, because you have a self-exciting effect. As the withdrawal of current increases, this spiral increases the strength of the magnetic field. Now, everything has got to be done with wood. We have a wooden frame. This is on a hydraulic crane, and now we're just about to lower one magnet on top of the other to glue the assembly together to get this kind of a combination. And there the copper disc is clamped between 2 of those discs of neodymium iron. Now, after you take that and you finish it, you wrap it first with graphite and then with fiberglass, and you smooth the whole thing down. And we have a 2-inch diameter beryllium copper shaft, and this is chosen because of its rigidity and its electrical conductivity. Very, very strong stuff. And we put the 2 of these together to get that. And they're screwed together in the center, and the center screwing them together puts, there's another picture of this, but this shows the bearings. There's a double set of bearings in either end. There are one's ball bearings, and the others are roller bearings to compensate for the heat expansion of the machine as it runs. This is a picture of the encircling copper bus bars with the slots cut in them, which forms the electrical contact between the rotating copper disc and the central end machine. And here is the completed rotor ready to drop into the machine. Now, what you see on here are 2 ridges which have been machined into this. And the distance between this and the surface of the magnet is an interesting parameter, because by putting a copper disc in the center of a magnet, copper is a little diamagnetic. It forces the magnetic flux lines out from the magnet. And also you have the flux lines returning around the magnet, and the 2 working together form a zone of no flux, about 3/8 of an inch above the surface of the magnet. And in that area is where you make your electrical contact with the liquid metal, so you don't have any magnetic forces acting on the liquid metal. Now here's a picture of the completed machine. This is an old aircraft generator run backwards as a motor. Vintage 1942, air-cooled, shunt to measure the current. We have a helium atmosphere in the box to get rid of the sludging problems. Everything's hermetically sealed, so there's no leakage. This is the kind of cables we use, although we have to use a lot of these cables. Each one of these is good for about 1,000 amps for a short time. On top are the reservoirs for the mercury. Here's another look. Here's the load resistor. We had to construct a load resistor to absorb 100 kilowatts at 12 volts. This machine is designed to put out 12 volts at slightly under 10,000 RPM. 2 copper bus bars and nichrome wires, about an 1/8-inch diameter. There's 144 or something on there. Here is the calculated performance of the machine. Now, what this shows is that at low speeds, this is the input and that's the output. But at high speeds, because of the efficiency of our drive motor is a variable, and I think we can safely assume our machine is about 3-to-1, but we're going to make a little bit more fine measurements on that. But taking all factors into consideration, measurements on the motor over the whole range, measurements on the generator in this lower range, we come up with a curve like this, which shows that we can make the thing run itself with the motor that we have if we get over about 6,000 RPM. Now, if we used a Faraday disc, we might be able to cross over at a lower speed. And this is a very, very conservative thing. All factors, bearings, windage, armature power and efficiency, motor losses, losses due to rotation of the magnet are considered, as well as their variation with speed. Now, all of these parameters are well known in electrical science. So So this is a very standard kind of measurement that you would make on a generator. It shows that if you make a machine which you can put out about 20 or 30 kilowatts, you've got the possibility of a self-running machine, because even if you have an electrical machine that has a 3-to-1 incremental output, that is, for every 1 kilowatt you take out, you only have to put 300 watts back into the drive motor, you still have all the fixed losses of bearings and wind and hysteresis and whatever effects we don't know. And until you overcome all of those and their rate of increase with speed, you see the ad machine output increases at the square of the speed, but the losses go about as the 1.5 power of the speed. So there is a point where you can get a crossover point and make a self-running engine. A lot of people are trying to do this. Now, this is Dr. Pappas, who I'm sure some of us have noticed. He came to my lab and he's making experiments on the forces which are not only exerted by the flow of current through the magnetic field of the machine, but also exerted by the current on the machine. And in our present understandings of electromagnetism, these are not understood. And I'll leave it to him to tell you about just exactly what he knows about this. We got to go to the next carousel. Now, I went to Europe about, I guess it's 3 months ago now. There was a conference in Munich at the Deutsches Museum, and there they brought together physicists to talk about relativity and gravity. There we go. I also met there 3 constructors of end machines in Europe. Now, this is the group which is the furthest ahead that I spoke to. Although there's many people who won't talk to me because they know that if they give me anything, I'll show it to the public. And so the commercial people don't talk to me, but the more spiritual people do. And this is a German group at a company, whose name you'll see soon. This is their drive motor. That's their machine. This is a picture of all the parts. It's copper plated. It's not made out of copper. The iron parts are copper plated in this. And this is their first machine. And in it was used ferrite. They used ferrite ring magnets. It's a Trombly con machine with a closed pan. They used 2 ferrite ring magnets, one inside the other, to provide the magnetic field. Now, the second machine they made, which I didn't see, but I did get the data on, here is a, see if you can get this in focus. This is made by a company called Rerum in Baden-Baden. And here's the test setup. You see, we use DC drive motors in our work. And the reason I have to use a DC drive motor is this. To balance a big heavy rotor is very hard, especially if it's intensely magnetic, because it saturates the sensors and it's hard to do. And we still haven't solved the problem of balance. So, and what that means is if you're not totally balanced, you just don't press the start switch and have it smoothly go up to 10,000 RPM. If it was not balanced, it would break everything up. With an electromagnet machine, you can make sure it's balanced without magnetism, and then we have a sunburst machine where you could have an AC drive motor of known electrical efficiency running at its known speed, as opposed to a DC motor of variable speed. Now, they're even more clever. What they used was an AC drive motor of known speed with a 3-phase variable frequency converter on it. So they could vary the frequency of the AC motor, or the speed, by varying the frequency. They went from 50 cycles to 100 cycles 3-phase. Very, very clever setup. And everything is carefully instrumented. They measure, as in the sunburst machine, they have metering brushes which measure the actual voltages on the outer and inner surfaces of their machine. And then they make measurements about the current flowing through the shunt and what actually comes out after you get the voltage drop in the brushes. And they are using these copper graphite brushes, which have about 0.2 of a volt drop. Now here is the original data of their second machine, and I have this data in written form. I don't want to go through this whole, what all this means now, but basically, as they vary the speed and the strength of the magnetic field in a machine which is electromagnetically excited, this is their second model. The picture I showed you was of their first. Their delta efficiencies go from 2.15, 1.7, 2.8, 2.9, 2.56, 2.27, 3.49, 2.88, 2.71, 2.71, 3.72. And at power outputs of up to, if this is what's going into the brushes, this is a combination of everything, total output, around 4 kilowatts max output. So the one we're making now, which is number 3, which is the one they want to produce, is the 30 kilowatt machine. This company is a company which makes catalysts, and they use a lot of hydrogen, and they want to use these machines for electrolysis of water to get the hydrogen at cheaper rates than they can buy it. Now, going on from that, one day I got a newspaper clipping about a guy in India, some Mr. Tewari, who's been seen here. And he had taken my results and replicated them in India. And he's had the press follow him, and we've helped each other a lot in getting information back and forth. And in 1977 or 78, somebody wrote me that I ought to contact this man with the results of what I was doing, which I did. And we've been pen pals ever since. And he had written me this letter. I've recently carried out certain experiments with machines similar to Trombly, and did find, and this is now July 4th, 86, did find that electrical power can be generated from space at efficiency much higher than unity, paper prepared by this subject. Now here's a verification. Trombly Khan also verified. And finally, there's a book we've been hearing about. Dr. Tewari has a theory about how this energy can be gotten from space by invoking a picture which postulates a structure to the electron, maybe due to the fact that we're describing it the wrong way. When I've discovered in my studies of rotation that when a thing is rotating, it not only rotates, but it precesses and it mutates, and all of these motions go along with rotation. So rotation brings into existence other motions besides simple rotation. So the real question is, we haven't really described rotation and all the higher orders of rotation, precession and nutation, which go along with it. And we're using cosines and sinusoidal functions to describe AC waveforms, which may not be the correct description. And if they're not, I don't know where that leaves us. You see, it's automatically been assumed that these circular functions adequately describe electricity. I don't think so. If the ideas which are classically derived out of the studies of precession developed by Euler in Germany back, I think, in the 1800s, are still used to describe things like the Larmor precession of electrons, electron spin, quantum spin effects. Now, if our description of precession is wrong, all of that information based on interpretations of precession is wrong too. So I think we're at a point in science where real basic changes are going to take place. After all, free energy is a real basic change. And I think that the real basic change should be reflected in our ideas about physics and our ideas about mathematics. Now, I'm not an expert on math. I'm an experimental physicist. And I can just want to suggest to you that a lot of the problems that we're having about understanding Tesla's work have to do with the inadequacies of our expressions of our knowledge of AC current. And that can be traced back to our lack of understanding of the precession of the gyroscope in terms of the information which has been developed from my experiments. So with that to think about, I guess we can close. Thank you. Am I supposed to answer questions? Is this what happens? Yes? Go on, all right. Yes, torsional pendulum. And I've always wanted to figure out a way how to get rid of back EMF. Now, I could do it two ways. One is to invent a new kind of motor. The second is to use the motor in a blocked armature mode where there's no back EMF. And at resonance, this armature is blocked and there's no back EMF. So it's an interesting idea which deserves to be looked at. But I am sort of, I don't know where I am. Maybe I'm coming into the mainstream in physics, but I have to raise all my money privately to do these experiments. This last M machine cost us $500,000 raised from charitable sources. Now, in something that's as important as this, I'd like to wonder why, what do they call it, the Department of Defense or something? Why don't they get interested? I don't understand it, but other countries around the world are. And the pressure is on us to do something about it. Okay, has anybody else got anything to know? What?
Why doesn't MIT get involved with that? Or the funding of it?
Well, I have this, maybe you think I'm moralizing, but I would say this, that people that work on ways of destroying the planet through radiation, germs, rockets, are not the creative sorts of people that would want to adopt a new form of science. They would much rather take our money and pursue these very theoretically empty, like the bigger accelerator and the super collider. And, you know, if you go to the idea that the physicists are creating their own particles with their own experiments, why build any more accelerators? And there's a whole echelon of people that want to keep the old thing going. They say, well, if you spend $15 billion, how can we stop? You know? So we have to get into something more life-sustaining than pursuing old ideas. We have to start doing some more thinking. So much of what Dr. Tewari will talk to you about, his insights on the structure of an electron, are based on insights. You know, if you read Einstein or read Eddington, they'll say mathematics always comes second. You have to have the insights to think, well, what would happen if I postulate a structure to the electron? You see, something below the uncertainty limit. You see, what does that mean? What does it mean if I look at forces from the idea of perfection and that you think that they're defective? What does this do for us? And it's these directions which are going to take us to new knowledge. I don't know what all the answers are, and I'm certainly not trying to be an authority. I've done some, I did something not too exciting. I applied all the known mechanical experiments to a rotating object. So that's not that exciting. What? Yes, sir. Get both of you. What?
Coming back to MIT, you said they didn't tell you about Faraday's disk.
No,
right?
never.
I have a feeling they're more linked with not having taught you any history of science.
That's totally correct. Because
There is, in fact, a 19th century theory there by Mach, which probably explains it all. Are you familiar with Mach's principle?
Mach's principle. Mach.
Well, people say yes, they are. But Einstein said he was familiar with it too.
Yeah.
But do you realize that Mach's principle means that, as my friend Phipps says, when the subway jerks, it's a distant universe that throws you down. At that very moment. Now, if that is correct, then all this is explained.
Right, but is that explanation accepted?
It's all explained. You don't need any free energy. You're drawing it from the distant universe.
Well, all right,
Okay.
fine. That's a good idea. You know, here's two thoughts. One is people ask me about free energy and perpetual motion, and I say, the only perpetual motion machine I know is the whole universe. If we can somehow tap into that, we've got all the perpetual motion we need. Second is, everything in the universe partakes of the properties of the universe as a whole. And what do we see when we look out in our telescopes? We see rotation, nutation, precession, higher order forms of rotation. Why can't we say the whole universe is rotating on all dimensions? And the motion of the planets is a reflection of that rotation.
Not only that, the main thing is momentum conservation.
All right, but you see, these are grand ideas. All right. Anyone else? Yes, sir.
For those who wish to do a simple experiment, they could refer back to Wilhelm Reich's replication of Galileo's attempts to watch the precession of the pendulum and discover that Wilhelm Reich observed that there are irregularities and that it led to his concepts of a free energy. One should not overlook his early research.
I'm not overlooking him, we just have so much time. He was one of the early workers in this field. Yes? Anybody, anyone else? Yes, sir. Eric, go ahead.
Yeah, have you considered that the loss incurred by the spinning magnet might be the hysteresis of the ether to that magnetism that it's spinning in?
Yes, and I've also considered there might be some inertial interaction. I think experiments should be carried out in outer space out of the gravitational field of the Earth, too. These are things that have to be done. Yeah. There is some intrinsic drag. We don't know what it is, we don't know where it comes from, and it could be some hysteresis phenomenon of the space. But then you have to postulate that there is something in space, and that takes you into free energy. Yes, sir.
You're saying you're getting more interest in the project now from abroad rather than in your own country.
Well, people are real secretive in America. Who knows, they may be perfecting an electric car right up the street. We just don't know. The people in other countries have other motivations. The people who come to me from India, when we discuss what is the purpose of a scientist, they and I agree that the purpose of science is to elevate the condition of humanity. Working on government programs does not do that. And so there are other moral imperatives operating in the world. We're only 6% of the people using 50% of the non-renewable resources. There are 4 billion people on this planet. They're going to, you know. Okay, Peter's busy. Go on. Does anyone else want to say anything? Well, look, yes, sir. Go.
Bruce, what's the future for old Friday?
I don't know. I would just like to make, I want to do 2 things. I want to build end machines and I want to teach physics. The 2 things sort of happen together. That's all I'm interested in. So people are coming to me who want to work on these projects, and there are other groups approaching me that want me to install systems, and that's what I do.
The 2 things really work together. It's like the end machine and the Faraday motor.
Yes, but they both came from the same mind. And if you realize that that mind knew nothing about what it was doing, if you read his original notes, it says, did many experiments. He doesn't tell you what he did, but he was moving this piece over here and turning that thing that way. And so when you're on the edge of the knowledge, there is no, you don't know what you're doing. Explanations come afterwards. Yes, sir.
Would you see any legitimate use for the super collider that's planned for eastern Colorado?
Look, I'm all for science and physics. I really am. But I feel that it may be premature. And that doesn't mean that I don't think it ought to be done. I think that what physics needs is more insight. Instead of looking at every particle in the universe as a billiard ball, it just collides on it without understanding these energy conservation. After all physics is based on mechanics. Mach started this off. Einstein picked it up. Our mechanical ideas are incorporated into our machines. That's how our minds work. If we have a deeper insight into the structure of the very particles, it's a new place to look. I would want to, in the way that the world is going now, I'd like to put the money in something more productive. I think the end machine is more productive than the super collider now, although there may well be experiments that can be done with it which are useful. But the priorities, yes, Dr. Thomas.
May my remarks on your end machine? Well, I would like to say the external circuit plays an important role in this machine. In one experiment I have performed, I was co-rotating the external circuit together with the whole machine, and there was no induced current in that case. In the last slide you have seen me at Bruce DePalma's laboratory. We were doing some experiments with the external circuit. By placing the leads in a certain direction, the braking was relieved. In other words, the load was less and the end machine was speeded up. Just a little percentage, but it did very clearly. That meant that the consumption from the motor was less. And then I expected that the output would be also less because the input was clearly less and the output was going to be, should be less. On the contrary, what had surprised me, the output went up by a small percentage also, which was showing a very, very strange effect. Much of this machine could be studied, and by the cardinal law of electrodynamics, by the original law of Ampere, immediately you will see the role that the external circuit plays there. And the correct electrodynamics are not derived by the Lorentz force law. By analyzing, you come to the conclusion that there will not be no braking. But analyzing the same end machine with the Ampere's original law of 1821, which I'm going to talk tomorrow, you find out that there will be a braking. There is a braking there, but there is no justification that the braking that is produced there will compensate all the mechanical energy which will pay for the output energy there. The differential test which Bruce has made, the way we have made there, shows that there is more increased output for less input there. But still, there is a problem. The machine has a lot of friction, and it seems to be like a play of nature there, that the friction is more than the usual output there. However, the differential increase, as Bruce has shown here, is a fact. I don't know how you can manage, Bruce would manage to make this a self-running machine in the end. But there is something there. Thank you very much.
Yes, sir.
Have you got any usable power out of what you've made already that you can measure and prove?
Oh, sure. Yeah, that's, that machine you saw taken out to about 20 kilowatts output. That's so
How
far.
much in?
Hmm?
How much power in and how much out? And
Well,
does it
the
have
overall,
range?
we haven't gotten an overall efficiency higher than about 80. Well, actually, the overall efficiency in our report at the speed that we're measuring it is slightly over 100. That is, including all the losses in the system, it's about 106%. But I got a report on that, which all the figures in. Let me give you a copy of that.
well, what I'm asking is, can you demonstrate, useful power production?
Sure. Sure.
No,
Not only I,
the
but
machine,
others.
not with graphs, not in paper, but with the machine.
Talk to the man who's right in front of you. He'll tell you.
I think perhaps
Why don't you have the machine here and demonstrate it?
I did it in Germany last year. I carried the machine from India.
Yeah.
Anyone else? Yes, sir.
Bruce, I was wondering, in all your extensive handling and experimentation with magnets, do you have any intuitive or observational feeling of what magnetism actually is?
All I can say is I think magnetism is a window into the free energy field of the universe. And what that means, you're just going to have to figure out. Yes, sir.
Bruce, in regards to funding this work, have you ever thought of approaching some of the major environmental groups?
Yes, I think we're about ready to do that because the worldwide interest has gotten to the point where we're for real. I heard from Adam Trombly via the president of this organization that there's a multi-megawatt end machine operating on the power grid in France right now. See, so yes, I do think the big environmental people should get behind this.
These machines are basically non-polluting, and that seems to be one of the major problems in the...
They're non-polluting, non-consuming, and they don't use any exotic materials.
Sir, could you ask the last question, please?
I would like to have the last question. We have another, yes. Anyone? Yes, sir.
What's the comparable cost for a new plant if you were to put in new equipment and replace old fossil fuel type system? What would it cost relative to the fossil fuel?
I think it would cost less because you have, not only do you have a simpler machine, but you only have a rotor. You don't have a stator. In a normal machine, you have to have these two pieces. This machine only has a rotor. What you do have to do with it is you've got to convert the low voltage up to something useful, which means you either have to drive a generator of the conventional kind or use an inverter. And so that's the extra piece.
Would you take questions?
I certainly will.
The House has asked us to close down so they can have their cleanup people come.
All right.
Please ask your questions in person.
Yeah, let's carry this on in a discussion. All right, thank you.
Here we're going to add the resin, which will react with the activator as we squeeze the whole pile together.
Yeah, we're trying to glue these magnet stacks together, and these guys are putting in the glue.
That looks good.
Yeah.
That sure stinks.
No, for chemical. Nice chemicals. Better living through chemistry.
How is it?
Okay, get out of his way.
Well, that thing doesn't like to close.
Okay. Sharing news.
Oh. There's a razor blade.
Somewhere.
Where's that?
Let's go high somewhere. Oakview, California. No, here it is. P.O. Box 1537.
Are you filming?
Trying to. Get near it.
But let's
Oh,
look.
okay, from over here.
Let's come from the mundane to the transcendental.
Actually, you can see how the flux lines are. Like this. See how it tilts?
Dear Bruce, I have come up with some information you may want to consider. It is from a high-placed, usually reliable source with access to government information who wishes to remain anonymous. 1. There is a conspiracy within the executive branch of the government to defeat the civilian use of end machines. 3. The CIA is in on the conspiracy even though technically this is nowhere within their jurisdiction. 4. There is cooperation between government and some of the big businesses such as General Electric, Westinghouse, and Exxon to defeat the end machine. 5. The Navy is working on the end machine as a means of ship propulsion. 6. The Air Force is working on the end machines for use in the Star Wars program.
Yeah.
7. The Army and the Marine Corps are clean, in other words, not a part of this conspiracy. 8. The FBI is clean and, as a matter of fact, is not aware of the conspiracy. It is so top secret and conducted on such high levels. 9. In order to maintain the conspiracy, those who are doing the hands-on work are not being made aware of just what it is they are working on. 10. The CIA cannot take any sort of direct action to stop the end machine, can make things difficult by being thoroughgoing pests in any manner imaginable. 11. Watch what you say over the phone. There probably is a CIA tap on your line. 12. In case your rights are threatened, contact the FBI. They are not in on this and will come to your assistance. This is beyond our humans' ability to handle. 13. The National Bureau of Standards was given direct orders to test Joe Newman's machine in such a manner that it would be sure to fail. This is all a bit frightening, but you should have the facts. The courts, of course, are not in on this and will render fair decisions. My brother, through his contacts in Washington, may be able to assist in running off some of this opposition. Patent anything you can concerning the machine. Without a patent, you may find yourself wiped out. Patent in any foreign country which will allow you to do so. You may have a market in such countries as Australia and New Zealand. If you can obtain patents there, for example, not to mention various European countries, even if your invention is stolen here at home. Again, my brother, through his contacts in Washington, may be able to assist you in obtaining a U.S. patent. Well, that's nice news.
Yeah. You get a couple letters like this every day.
The Army's
Well,
clean.
the Army's clean.
They're
The-
still
the
driving
Marines
around in
are
their
clean.
Chrysler tanks.
Oh, that's nice.
God. I wonder how we're going to put
I have
Teflon pushers down there anyway, right?
Yeah, the bottom doesn't have the bottom quarter inch is okay. It's
Yeah.
just the sides around the top that have to be really clean.
Well, what do we do now, gang?
Well, we either glue up another stack of 3 or
This is no different than atomic energy.
you get a little bit of a cone on the top, so not 52.5. Making sure that the polarity was in fact what it's marked so that we don't have any anomalies from screw-ups.
Checking the polarity and
Then we bring it down
on the
onto here,
plate.
which it really wants to grab onto. Okay. We haven't cleaned this one.
So these are all lined up and cleaned. They have been cleaned.
These are our spacers for doing this particular row. For this row, we didn't use any spacers.
So we'll push forward on these. A cap keeps these from jumping off the surface.
They don't want to be pushed together, and so just to make sure they stay there. Okay, you got it. Where's the other wrench? Are you tight? test it out.
Set it right over here.
Yeah, okay, let's take it over there.
Left side.
A small crowbar. So this is the second one.
Do that again.
Finish with this bit?
Yeah.
Now we're talking.
Polar literature on anything? You find it's all been classified since '82.
I know I didn't find it in any of my physics books.
No, I mean, but
I know, the top project.
Yeah, don't you have computers that interface with like the NASA library or something?
Yeah, I know what you're talking about.
Well, if you try to access any information on homopolar generators after '81, it's all secret. So this is just a really strange.
I don't know. I assume he designed it.
There ought to be some way to get that changed, and that patent application ought to be the key thing that'll do it.
Well, that patent application was gagged by Harold Brown. See, and the way that happened was that the lawyers that submitted that patent application made foreign applications at the same time. And when the classification order came through, they could only grab the copies that were in this country, and the ones that had been sent out to the foreign, whatever they do, Patent Cooperation Treaty Organization, that was still extant. And one of my people in Europe went through a computer search and located that and sent it to me, and I circulated it.
Well, now that that's back in this country, the authors of that should be able to take it to the government and say, now look guys, here it is, it's public domain, lift your gag order.
Well, what happened was they went to their lawyers, and the story that I got was that Trombly was approached by several secret agents and wanted to know whether he had released that information because he had been gagged not to. And he said no, he hadn't done it. He was very angry at me for having done it at first, but then once all the word got out, he consulted his lawyers and they told him, well, now it's public information. The gag order is no longer applicable. And so since then, he's given 2 talks on it. One in San Diego last December, and the other one at this German conference in Hanover about a month ago.
Okay. Have they done any more work since 80 or 81 when
not that I know.
I can't imagine NASA not having done something.
Because the I got a call from a NASA scientist that there's a research center in Maryland somewhere who was interested in this. He was an atmospheric scientist, and he wanted to know about this kind of end effect in the atmosphere. And I said, yeah, there's one from the rotation of the Earth. It's 1,000 volts between the pole and the equator. It's generated just due to the rotation of the Earth as a rotating planet. And he said, that's very incredible. You couldn't move he said, do you have any more information on this? And I sent him a copy of that patent. And he said, well, The people around here would
No,
freak out and
this
say,
milling machine at 50 degrees on
No, there's a 3/16 tool holder this big that went down, and then there's a 5/16 carbide boring bit that sticks out of the thing and it spins.
It spins around. Okay.
And the only way we were able to beat that was Bruce put a little rubber thing on the back so that it would rub on the other side. So it's sort of in there and tight.
Right. Tight.
Yeah.
the rail gun.
Yeah, and cut it that
Rail
way.
gun for the
It's just a real pain in
Army.
the milling machine.
And,
You take a screwdriver up, you can stick it.
I've seen some unclassified stuff in Aviation Week and elsewhere on rail guns and this kind of generator. But
yeah, it was really radical.
you know, it's just broad brush articles. It is
Right.
admitted that they are working on it.
Oh, yeah. So,
And as a matter of fact,
Pardon?
I would just love to be able to find that article now because it told the name of the company that is building these generators.
oh, I know what the name of the company is. It's in Texas, and it's a company that's been set up by Dr. Woodson, Herbert Woodson, who used to be the former head of the energy laboratory at MIT. He was one of my professors at MIT. It's at the University of Texas in Austin in the electromechanics laboratory. And they developed this railgun generator based on a one-piece machine, but actually it's a two-piece machine and they get dragged. I can explain why. It's not a one-piece end machine like we're making. It actually has a rotor and a stator. And that's why they get the drag. But anyway, they're manufacturing this thing for use in the railgun. And they set up a company on the side. Once they had developed it on a DARPA contract,
the rubber thing worked.
he set up his own little company on the side to manufacture these machines.
I think I saw one advertisement for
Yeah,
that company.
yeah, it was in Magnets, in fact, I think, or was someplace. I saw it too, and I called the company once and I said, "Don't you want to improve your machine?" Yes. I wrote a letter to your boss or whoever it is and said, "We've seen this thing and it does this, that, next thing. You could not do
It
that."
was cutting deeper and deeper as it went in, and I think he was backing it off a little bit. Or no, he couldn't.
Well,
See, the R&D, I used to work in government R&D back in the 60s, and it was those are the good old days, and everything was going full blast.
Yeah.
What's happening in the 80s is everything is a dead
But it's
stop.
also held intrinsically.
And I don't know how companies work anymore. I don't know. See, and if I had brought this to the head of my companies back when I was in it, they would have gone for it in a minute. I can't understand.
I would like. I know one guy who's in the hierarchy at Rockwell and Downey. I would like to tell him about this for a couple of reasons. One, because I would like to see his reaction and see Rockwell's reaction to it, because he's close enough to the innermost circle that he can talk to.
You might
the right
ask him
people.
if they might have already made a study on it, because I think one of those aircraft companies already has, and it was reported back to me that we studied you completely, and we decided not to go ahead. And I said, why not? This is too big for us. We don't know what's going to happen with the government. And that's what I've heard every time. So
I really wonder where we can't get, let's say, grants for this, or why universities aren't excited about the potential of being able to work at it.
because the existence of a real free energy machine is a completely discombobulates all the known theories of electricity. And the other measurements I've made on inertia and inertial fields and things like that it's new information. It's not like it's contradicting anything. You're adding something to the known pile of things we know. And when you do that, it has to rationalize with everything else we know. And some of the other things we know tell us that what this new information is telling us is impossible. You see, so if you say you have some physicist called me up last week and he said, this is very important. He said, this is going to cause profound changes in physics. And he says this means non-conservation of charge. He said, you know, in normal theories, for every electron that you produced, you get a positron produced. That's how the theory of electrons is developed by Dirac. And in terms of electrical machinery, they don't create electrons, they pump electrons. This machine actually liberates them from space. Now, the non-conservation of charge. There's free energy in physics. You can somehow bring a charge out of the vacuum with a rotating magnet generator. So all these things strike fear into the hearts of those who don't want to see any changes. And if those changes could affect their job, then...
Have you gotten a call in the last 2 days from a girl?
Made in San Clemente.
What happened?
Slipped down the slot.
Okay. That was interesting, Bruce says. We're having
cardboard that both Josh and I dove across the
Yeah.
top of the sheet.
That was a funny one.
We didn't get hit.
We were out of the way of that cardboard in case it hurt us.
That cardboard cover and the one that was on the floor, we set the other one down on the floor and we're sliding across, and the cardboard fell.
Big piece of cardboard. We're down low like this and we just see it fall towards it. What was going through my mind is I was thinking, but we're 4 or 5 feet away. It's not supposed to happen this far.
This has to go.
Yep. Oh, you're in first, I trust? Now, how we do it so it gets on the steel only? Excellent.
Yeah. We gotta clean it a bit, and I'll get silver paint.
Yeah, we gotta do the inside and the outside of it.
Put the coupling on first, and then we'll clean this good too. Yes, comrades, we use lots of silver. We buy it from the contracts. Slap them together. Stir for a little while.
And bake at 670 degrees centigrade for 4 hours.
100.
Trouble. We're going to take one and I could look at it.
Okay, photo opportunity over.
Don't take it off yet. Can't touch any tighter up holes during that. Well,
It looks like what it needs almost is to have one end loose and just tap one end, tap this base over in this direction a bit.
Output voltage,
192.
okay, we got 9.9 novolts and 15.3.
got it down, 191. We're at
15.20. Okay, 18.5 volts.
of the DePalma Energy Corporation. And this tape is a documentation of a report which we have issued, the DePalma Energy Corporation Report Number 1, 6 January 1988, on our initial tests on our N1 electrical generator, which is right here. Now, it would be better for those looking at this tape to have read this first, but in any case, I'm going to go over the complete system in detail. So what will be recorded here is a record of the experiments which is given in this report, so you can see how all the measurements were made and how the machine operates. The N machine is an application of a principle discovered by Michael Faraday in 1831, when he discovered that you could extract electricity from a rotating magnetized conductor by taking the electricity from the outer edge of the conductor and from the center, where the magnetic field was parallel to the axis of rotation. Now, in 1978, we constructed the first small models of this machine, and eventually were able to construct the model which is the prototype of the machine you see here. And it all started with this machine, which consists of a 6-inch diameter stack of ferrite magnets with a copper disc sandwiched in the center of the stack, and it can be rotated with a motor, and the electricity can be extracted. And the electricity can also operate a Faraday disc motor. It is part of the same assemblage, and we can explore the parameters of a self-running machine combination. But all the machines that will derive from this all require an N machine generator, a generator that produces more electrical output than the mechanical input into it. Now, this machine, as far as our measurements show us, is doing somewhere better than 3 to 1. And what we've done here is to double the size of the magnets. Those are 6-inch diameter rotor. This is a 12-inch diameter rotor. Actually, it's with an iron end plates on either side of the magnet stacks that comes out to 13 inches in diameter. And 2 N machines are put in series on the same shaft. And the magnetism in one machine is reversed, so that we have north-south, south-north. So rotating the machine will produce an electrical output which is, in this case, positive for a counterclockwise rotation, and this pole will be negative. And the voltage is developed negative, positive, negative, positive. So the 2 machines are in series through the central shaft. And as described in the report, the center of these 2 machines is connected by a 2-inch diameter beryllium copper shaft, which is in tension, compressing a 6-inch diameter aluminum cylinder with a 1/2-inch thick wall, so that the center section of this machine is stressed and is stiffer than the solid piece which could replace it. So we have a pre-stressed center section. We have 2 13-inch diameter magnet stacks, which are 8 3/8 inch thick. And each stack contains about 200 pounds of neodymium iron boron magnets in the form of hexagons, which are 2 inches across the flats and 1 inch thick. These magnets are glued together into a large hexagon. Some of the hexagons are sliced in half, so we have an approximation of a circle. And then that is then made into a circle by metallic putty encircling that, and then we encircle that combination with a 1/4 inch of graphite fiber, and then another 1/4 inch of fiberglass, the fiberglass being slightly more elastic than the graphite. So that combination, I feel, will contain this structure up to about 10,000 RPM in its present construction. The rotor itself weighs about 800 pounds with the shaft and the 1/2-inch thick steel end plates on the sides of the magnets. There's a 3/8 inch thick 14-inch diameter copper disc in the center of each stack. And as is shown in the report, the stack of magnets has a self-energizing feature. That is, the copper disc, which is in the center of the stack of the magnets, is cut into a spiral, actually two spirals, which give two-turn windings in parallel in each stack, so that when current is withdrawn from the machine, the magnetism is increased. So it's a partially self-energizing machine. That's necessary in a machine like this because by putting the magnet stacks in proximity to each other like this in the opposition where we have north, south, south, north, then there's a demagnetizing effect of one stack on the other, which is around 20%. So to make up for that and perhaps even overcompensate it, we have put in the self-energizing feature originally suggested by Tesla in 1891. Now, the way the electrical contacts are made are through two liquid metal, metallic mercury contacts, one here and the other here, which consist of a 1.5 inch wide by 1 inch thick copper circular bus bar which encircles each magnet stack, and into that bus bar is cut a channel which is slightly wider than the 3/8 inch thickness of the copper disc in the center of each magnet stack. And mercury is inserted into that channel so that it forms a bead between the rotating copper disc and the rectangular channel which encircles it, a picture of which is given in this report on the second page, if you can focus in on that. You see that down on the bottom, the way the mercury channel is cut into the copper bus bar. Okay? Now, the mercury, which is fed into the channel, is in these two polyethylene vessels, and we can regulate the flow by a combination of turning this valve and the size of a tiny orifice underneath which regulates the flow of mercury into the machine. And in this combination, what we do is in order to operate the machine, we put the mercury in like this. And if you're careful, as we've learned to be over the years, we don't spill any. Now this machine is hermetically sealed so that even though mercury vapor is toxic, although its toxicity may be somewhat overrated, no vapors can escape from this. And on top of that, we try, for certain of our experiments, to maintain a helium atmosphere in this box, which prevents sludge forming on the mercury, because the mercury in contact with the air does oxidize and a sludge builds up. And we have to, really what happens here is that in the operation of the machine, a certain amount of mercury is lost, which we have to shoot in a few cc's every few minutes. And that, which goes through the brush system, accumulates on the bottom, and we drain it off, and we clean it and recirculate it. So, in a sense, the fact that a little bit leaks out is a good idea because there can be a continuous purification system going on to take the sludge out of the mercury. Otherwise, the mercury system is a perfect electrical power takeoff system. The drag is infinitesimal and the resistance is very low. We've had no troubles whatsoever. We have explored the magnetic field on the outside of these stacks, and the mercury contact takes place in a region of zero flux, so that when a current is withdrawn, the mercury doesn't have any forces acting on it through magnetic interactions. Now, in order to test this machine, we have to have an electrical load, and that is connected to the machine through the output terminals, and there's another identical set on the opposite side because this machine was designed for 10,000 ampere service. So two sets of bus bars are needed to remove the current, and this cable, which is rated for 200 amps and we run at 800 is suitable for our experiments, but to completely understand the limits of the power of this machine, copper would have to be used. Now, the internal resistance of this machine is 75 microohms at 800 amperes. And as I understand the self-energizing feature, that internal resistance may drop as the current increases. So in a pulsed operation, this machine is probably capable of producing extremely high currents, perhaps even, well, at the 75 ohm internal resistance and with a direct short circuit across here, you get more than 10,000 amperes per volt. So 10 volts at 100,000 amperes is a possible pulsed rating for this apparatus. What that would be used for, I don't know, but that's what it's capable of. Now the current is taken through these heavy copper cables over to a special load we have constructed to absorb 100,000 watts at 10 volts. And this consists of 1/8 inch diameter nichrome wire, which is connected between two copper bus bars, 1 inch thick, 1.5 inches deep. And they're 64 tines inserted here with a calculated resistance such that we would achieve 10,000 amperes at 10 volts. So that would be the 100,000 watt rating of the machine. The current which flows in this circuit is measured by what's known as a shunt, and this has a certain amount of measured resistance in it between these two heavy copper blocks and is calibrated in this case to give us 50 millivolts for every 800 amperes that passes through. And the shunt that's in use is right over here, which you can't see too clearly, and the current is read on this meter. Now, for those purists who look at this, they'll say, well, this isn't too accurate, but we've checked this with our digital equipment, and when it says 800, it's 800. So for the purposes of this demonstration, we'll look at this, but this has been verified with apparently far more accurate equipment, but nevertheless, this is accurate. Now, what drives the machine? Here we have a war surplus aircraft generator, which was used during the Second World War. It was rated at 500 amperes, 30 volts. The speed of operation was 4,000 to 8,000 RPM, and the output voltage was probably regulated by control of the field excitation, which is nominally 24 volts at 12 amperes, which is supplied by a power supply on the other side of the room, which we'll take a look at in a minute. Now, this motor, which is the generator run in reverse, which we're using, has 12 poles, and between each pole is an interpole. And the purpose of this complex construction was to assure that at high speed operation there wouldn't be any losses in the commutator because of excessive voltages between adjacent commutator bars. Now this was important in 1940 when this was made, but it's not important now. But the inclusion of these extra poles does reduce the efficiency of this machine, so that as a motor it's not terribly efficient. I believe basically that as a motor we might be able to do 80%. And that's how our calculations have been carried out as a maximum efficiency for this machine. The current is measured also by another shunt of the same kind I've shown you earlier, and the voltages are now read on these meters on this side of the room. Let's take a break for a second here. As I was saying a moment ago, the voltages and the currents in this setup are measured by instruments on this table. This oscilloscope looks at the output of the end machine. We block out the DC voltage, and this is on the 50 millivolts per centimeter scale. And when we see large breaks in this curve, we know that we are a little low on mercury and we put a little more in. I'll demonstrate that in a while. Over here, we have a 300 millivolt meter full scale, which is measuring the millivolts developed across the shunt, which is monitoring the motor current. And since this is on the order of 100 or 200 amperes, we wanted a high accuracy measurement. So the voltage measured across this shunt is read by this meter in amperes, and also by this meter in millivolts. And to convert the millivolts here into amperes, you multiply by 16, because it's 50 millivolts for 800 amperes. This meter measures the output voltage of the end machine. It's on the 12 volt scale divided by 2, so that's 6 volts full scale. And the operating point which we have established for the first run of our experiments is 2600 RPM, which comes out around 3.1 or 3.2 volts, as you'll see. This is the voltage applied to the motor, which is read on a very coarse way on this meter, but more carefully on this on the 60 volt scale. And the motor voltage will be on the order of 25 or 26 volts. So we expect readings of 25 or 26 volts here, 3 volts here, 100 amperes or so here. And the speed of the machine is measured by the strobe attack, which has been recently calibrated. And so with the flashing light, we stop the motion of the shaft, and we can read out exactly how fast the rotational speed is, and we can do all our measurements at exactly the same speed. So if it's 2600 RPM plus or minus 1 RPM, they'll all measure, even though we'll set the thing at the same place, so all the speed measurements are at the same speed. Now, over here, we have 2 power supplies, one of which is not used, this one. This one, which is used, has 2 outputs. One output is being used to supply the 24 volts field excitation for this motor. Now, we also have on this a contactor, which may not be visible at the bottom, a 1000 amp contactor, so we can control the current into the motor and turn it on and off with this switch. And the motor current is coming from cables, which I don't know whether we can see snaking along the floor here, but outside here we have a 60 volt, 600 ampere capable diesel electric generator to power this apparatus. And so the current is generated outside. We regulate the voltage of the current at the machine to operate this machine at whatever speed we desire. We keep the field voltage constant at 24 volts. We don't change that. So these are totally different operating conditions than for which this was designed. And our future plans, as I've outlined, consist of inserting in this shaft coupling a torque measuring instrument, which will directly read the input torque, which is turning the end machine. Then, by knowing the exact speed and the torque, we can get the exact horsepower input, and then we will know the exact voltage and current. We will have the exact electrical output, and through the relationship of 1 horsepower equals 746 electrical watts, we can determine the true and exact power gain of this machine without having to rely on any kind of speculations of what we think the electrical efficiency of this thing is. Now, this is an air-cooled unit, and the air cooling is provided by a blower, which we may be able to see over here. And that blower exhausts outside and sucks the air from these holes through the windings and outside. This whole setup is cooled by a blower, which you're seeing right now, and the air is drawn through these holes cut in the front and flows through the windings. Now, to get back to this machine, one thing I haven't spoken about at all is the intense magnetic field which exists around this machine. Now, I can illustrate that in a very simple way by taking one of these wrenches, which you have in the shop, and if you bring it close to these things, it's almost pulled right out of your grasp. Now, what made the construction of this machine so difficult is the fact that the magnets which compose each one of these rotors are the largest magnets that can be magnetized with the magnetization equipment presently available. And that means that the rotor has to be assembled as a magnetized piece. And then all the machining operations have to be done on this big magnetized stack. Now that makes for extreme difficulty in a machine shop. Every move has to be planned, and cranes have to be used, and if the machine gets away from you and sticks to something, you have to pry it off. So that makes construction very, very time consuming. Every move has to be taken very carefully. The other part of this is that this rotor is suspended on two sets of water-cooled bearings. There's a water-cooled ball bearing on this side, double roller, angular contact. On the other side, we have roller bearings, two sets, double row. Both sets are water-cooled. Now, when you take a piece like this to be balanced, and they put variable reluctance sensors on this machine, the magnetism is so strong around the ends that the sensors are basically paralyzed. They don't operate. And so we have had a very difficult time perfecting the balance of this rotor. And for that reason, we have not been able to run it up to the 7 or 8 or 9,000 RPM, which it's capable of. So our experiments at this time are 2,600 RPM. But we are refining this balancing process so that eventually there will be no vibration at all. And so the limit of the machine will then be the explosion point of the rotors when the centrifugal force is built up to a point where the graphite can't hold it together anymore. But in the construction of this machine, the hexagons were glued together with special adhesives developed specifically for gluing this type of material, which were phenomenal in their strength. But nevertheless, the forces between them were so strong that a huge press had to be involved in the operation, and a long, hand, time-consuming operation it is. Nevertheless, we built up the rotors and we assembled the machine, and here it stands. The reason the shaft is beryllium copper is because we don't want magnetism coming out the ends of the machines into the motors or whatever is attached to it. And also, beryllium copper has, in its annealed state, can have just almost the resistance of plain ordinary pure copper, but the strength of beryllium copper. So it's very good for the electrical conductivity that we want to achieve here. The disadvantage of it is that it's very elastic. And that gave us special problems because all the beryllium copper should be heat treated to totally relieve it before any machining operations are done on it. Also, the use of mercury in a machine like this has to be thought out carefully because mercury dissolves certain metals, and our experiments have shown us that copper is compatible with mercury and there is dissolving. There's amalgamation but not dissolving. But the mercury doesn't touch anything else but polyethylene and copper. We had no difficulties in that regard. So what we're going to do is I'm going to run this with no load, and then I'm going to unscrew this cable connection and just turn on and off a current of 800 amperes at 3 volts. And you can see the effect on the machine will be very slight. And then I will close the circuit and increase the drive power, and we'll run the machine up to 2,600 RPM, the same RPM we started out with the no load, and we'll show you the increase in reading on the meters. Then, after this is completed, we'll sum up what we looked at here. All right, so let's go to the next phase where we're going to run the machine at 2,600 RPM without any load.
the 50 millivolt per centimeter scale shows a little bit of ripple. Our output voltage is 3.25 volts, and the motor voltage is 25 volts. Motor current runs about 90 amperes, but it's 16 times the reading on this scale, runs 5.6. Now, what I do here, I'm going to put a little mercury in. And down here, I have the cables, and if we short like thus, see those spikes? That mean we haven't put in enough mercury. So this ought to do it. More. All right. 800 amperes over. Well, you can see the voltage on the 3-volt scale. You on that meter? Short it, unload it, short it, unload it, short it. Now what we're going to do later is we're going to adjust the motor so that it compensates for the slowing down. There's a little slowing down. We're taking 2,400 watts out. Have you shown this meter over here? All right, we go no load, full load, no load. Now the real way to do this kind of a thing is to keep the load on the machine steadily and look at the current change on the drive motor when we connect these cables together permanently. We'll do that in the next tape. Now we're running under load at 2,600 RPM. The voltage output is on this meter. You can zoom in on that one. It's about 3.1 volt, 3.12 volts. The speed is 25,600. So you can scale these numbers a little bit. Voltage output on the scope. Speed fluctuations, which I think you can reduce a little mercury. Motor voltage. 25.3. 25.3. Motor current would be 16 times 12.6 at the present, but it's dropping as time goes on. Eventually goes
loosen up, the drag decreases. What I'm going to do is shut the system down now, and we can have a little discussion of what we've been looking at.
Of the N machine.
Right, the N machine, N is a number like the nth degree, and this very simple machine has so many possibilities to it that when I got the idea for it, I thought, well, how could I possibly describe it? And the letter N, capital N, seemed appropriate because it means the nth degree or n dimensions or any number which is large. So that's how it got named. And what it's the result of is that I am a basic physical scientist, and that means I'm interested in kinds of simple little problems, like how much things weigh and how fast they travel and stuff like that. And I did a number of experiments a long time ago, 20 years ago. Most of the professors in science recoil at the idea that there might be anything new, because so many thoughts have been thought since the beginning of scientific experimentation. It's hardly likely that anything new will be discovered. And
that's why they wanted to close the patent office about 90 years ago.
That's right. They thought they had all the basic problems solved, but the basic...
They always think that.
I know, but you see, yes, I agree with you. It's hard, what can I say? But the real basic problem is man itself, because man has certain implicit assumptions he makes about things, and those are the real basic problems. And they're the things that prevent us from doing certain little simple things, like thinking that rotation might be different from non-rotation. But anyway, to make a long story short, I worked on this material for studying rotation for about 10 years, and I did develop some very interesting experiments, but I couldn't get the physics community interested in them at all. And especially because my experiments invalidate the general theory of relativity and open the door to things like free energy. And this is very, very basic stuff, and most people just don't want to deal with it. So then, being that I always had been interested in electricity, I tried to think up some kind of electrical phenomena that would represent all the new things that I had learned about rotating objects. And so then I decided, or I got the inspiration, or somehow it was channeled to me that a magnetized gyroscope or a magnetized flywheel might have some interesting properties. And so the very first experiments I did on the magnetized flywheel, which is a form of electrical generator, have developed into what's known as a free energy machine, which produces more energy than it takes to turn it. And that's opened up a whole new technology. And I guess what we're leading up to is the fact that all the years I've been pursuing this work and trying to circulate my results through the underground journals have had an impact around the world. And I went to Germany, having been invited to an international congress on relativity and gravitation, which was on the 22nd, 23rd, and 24th of last month of April, and to give a paper not only on the N machine, but all the physics that led up to it. And this was a really fantastic experience for me and an opportunity, because while I've gotten the total snub from all the physics journals and the professors and people who were asked to comment on my work in this country, I walked into a situation in Germany where not only they received me with open arms because of my physics, but there were already 3 groups of people at this conference that had made my machine and had replicated my results. That is to say, they got like 3 to 1, 3 times more out than in, and 2.5 more than out than in, but anything over 100% is pretty fantastic. So I went into a situation which was very receptive, and this was a congress that that had people from Russia, America, all the countries of Europe. And these were the kinds of professors that walked around in black suits and black ties and white, very professorial types. And to have this going on in the Kepler room, in the Deutsches Museum in the center of Munich, nothing could be more venerable or dripping with the hallowed traditions of physics.